Hello, everyone. Welcome to a lecture on Introduction to Unsupervised Learning. In this session, we're going to look at the basics of unsupervised learning, its key algorithms, and their applications. Overview. To give you an outline of what we will cover today, we are going to uh, look at the definition of unsupervised learning and how it differs from supervised learning. Then we are going to look at key concepts like clustering, dimensionality reduction, and anomaly detection. And we're also going to look at some common algorithms used in unsupervised learning and uh, explore practical applications. And then we're going to look at advantages and challenges of using unsupervised learning. What is unsupervised learning? So unsupervised learning is a type of machine learning that deals with data that doesn't have labeled responses. So unlike supervised learning has input-output pairs to learn from. Unsupervised learning, its goal is to find hidden patterns or intrinsic structures within the data. It is especially useful when we don't know what we're looking for in the data or when labeling data is too expensive or time-consuming. Supervised versus unsupervised learning. So in supervised learning, the model is trained on a labeled data set. It means that each training example is paired with an output label. So the main goal is to learn a mapping from inputs to outputs that can be used to predict labels for new data. On the other hand, unsupervised learning works with unlabeled data, and the goal is to explore the underlying structure of the data without any predefined labels. So this makes it powerful for tasks like clustering, where we want to group similar data points, or dimensionality reduction, where we want to simplify the data while retaining its essential characteristics. Key concepts in unsupervised learning. So um, we want to look at some key concepts in unsupervised learning. First, clustering involves grouping data points that are similar to each other. Second, dimensionality reduction reduces the number of variables in the data while preserving its important features. And lastly, anomaly detection focuses on identifying data points that are significantly different from the majority, which can be useful for detecting outliers or rare events. Clustering. So clustering is the process of partitioning a set of data points into distinct groups based on their similarities. This is especially useful in applications like market segmentation, image segmentation, and document clustering. Common clustering algorithms include k-means, hierarchical clustering, and DB-scan. And each of these algorithms has its own approach to grouping data points and can be selected based on the specific requirements of the task K-means clustering. So K-means clustering is one of the most popular clustering algorithms. So you basically want to look at the data set and partition the data set into K clusters, K being uh, the parameter. And just to give you a brief steps, here's how it works. You first want to initialize K centroids randomly, and then you want to assign each data point to the nearest centroid, and you want to recompute the centroids as the mean of all points in the cluster, and you want to repeat the process until the centroids no longer changes significantly. And uh, K-means is widely used due to its simplicity and efficiency, but it requires specifying the number of clusters in advance and may not perform well with non-globular clusters. Here, we're going to have another lecture going over these in detail, but just to give you a brief idea how it works in Python scikit-learn, you want to import k-means from scikit-learn cluster, and we're going to create sample data using NumPy array. And given this sample data, you could run k-means and specify a number of clusters to be 2. This means that we are setting k to be 2, and we're providing random seed of 0, and then we're going to run fit with sample data. Then if you print labels and cluster centers, you'll be able to find out what the result of this k-means clustering is. Now we'll move on to hierarchical clustering. So hierarchical clustering creates a tree-like structure of nested clusters. So this clustering can be performed in 2 ways. First one is bottom up, second one is top down. And this way is often called as agglomerative clustering or divisive clustering. So in bottom up clustering, each data point starts as its own cluster, and the closest clusters are merged iteratively until all points are in a single cluster. And in divisive clustering, all points start in one cluster and splits are performed recursively. So this method can be advantageous because it doesn't require specifying the number of clusters beforehand, unlike k-means clustering. So that's the advantage. And the resulting dendrogram can help understand the data structures. So here's an example. We have a sample data, then we import a dendrogram and linkage from SciPy cluster hierarchy. And given the sample data, we're going to call linkage with sample data and specify parameter to be word, and then call dendrogram, and we're going to use show this result. We're gonna discuss more in detail on lecture on hierarchical clustering, but just for now, just wanted to give you a simple example. DB-scan. So what is DB-scan? DB-scan stands for density-based spatial clustering of application with noise. So DB-scan identifies clusters based on the density of data points, and which makes it suitable for discovering clusters of arbitrary shapes and handling noise effectively. So this algorithm has two key parameters. First one is epsilon. Uh, Epsilon defines the radius for neighborhood points, and um, min points, which is the minimum number of points required to form a dense region. DB-scan is particularly useful in applications like geographic data analysis and network security, where traditional clustering algorithm might struggle with noise and irregular cluster shapes. And here is a Python code example. You can import dbscan from scikit-learn, and as we said, there are two parameters. So you can specify epsilon and min samples, which is min points. Dimensionality reduction. So dimensionality reduction aims to reduce the number of variables in the dataset while preserving as much information as possible. So this is important for simplifying models, reducing computation time, and mitigating the curse of dimensionality. So common techniques include principal component analysis and t-distributed stochastic neighbor embedding. These methods help visualize high-dimensional data and identify the most important features. Principal component analysis. So principal component analysis is a widely used technique for dimensionality reduction. It transforms the data into a set of orthogonal components called principal components, which are linear combinations of the original variables. So the steps involved in PCA are first, you want to standardize the data. Second, you want to compute the covariance matrix. Third, you want to calculate the eigenvectors and eigenvalues of the covariance matrix. And fourth, you want to project the data onto the principal components. So principal component analysis is used in applications like face recognition and genome data analysis to reduce data complexity while retaining essential patterns. And here is an example of using PCA and Python on very simple data using scikit-learn. We can import PCA from scikit-learn, and then can set number of components to be 2, and then you can call fit transform and provide sample data as a parameter, then you can get principal components. T-distributed stochastic neighbor embedding. It's also called as TSNE, is another powerful technique for dimensionality reduction. This is particularly used for visualization purposes. So this converts high dimensional data into a lower dimensional space while preserving the relative distance between data points. So the algorithm works by calculating pairwise similarities and converting them to probabilities, then minimizing the divergence between the high dimensional and low dimensional representations. So t-distributed stochastic neighbor embedding is commonly used to visualize complex data like images and text in 2 or 3 dimensions. And if we're going to go more in detail on a lecture on this, but just to give you a brief overview, you can import TSNE from Python scikit-learn library, and you can initialize TSNE with number of components, then call fit transform method, provide sample data. Anomaly detection. So anomaly detection is the process of identifying data points that deviates significantly from the majority of the data. And this can be really important in applications such as fraud detection, network security, and fault detection in manufacturing. So common methods for anomaly detection include statistical techniques, distance-based methods like k-nearest neighbors, and density-based methods like local outlier factor. So each method has its strength and is chosen based on the nature of the data and the specific application. And just to give you a brief example, we're going to show you the density-based methods, a local outlier factor. So in scikit-learn, you can import local outlier factor, and given the sample data, you can initialize local outlier factor with number of neighbors, and then call fit predict on sample data. Applications of unsupervised learning. So unsupervised learning has numerous practical applications across numerous fields. For example, in customer segmentation, it groups customers based on purchasing behavior to tailor marketing strategies. And in market basket analysis, it identifies products that frequently co-occur in transactions. Anomaly detection helps in fraud detection by identifying unusual transactional patterns. And data compression reduces data size for storage efficiency, and unsupervised learning techniques are also used for pre-processing and feature extraction in image and speech recognition. Advantages and challenges. So we looked at unsupervised learning and saw that it offers several advantages, such as not requiring labeled data like supervised learning, and it helps in discovering hidden patterns, and it's being useful for exploratory data analysis. However, unsupervised learning also comes with challenges. Evaluating the results can be difficult because there are no ground truth labels. The interpretability of clusters and components may be challenging, and meaningful insights often require domain knowledge. Conclusion. So in summary, unsupervised learning is essential for discovering patterns in unlabeled data. So unsupervised learning includes techniques like clustering, dimensionality reduction, and anomaly detection. And these methods have wide applications from customer segmentation to fraud detection. Uh, While unsupervised learning has its challenges, um, it is still an invaluable approach in machine learning. Thank you, everyone, for listening.